Okay, so we are ready to follow our last lecture.
Yes, thank you.
Unfortunately, of Filippo. So please, sorry. Yeah, it's the last one.
I mean, if you want, we can do a special one for you, Augusto, tomorrow afternoon.
On Saturday. Okay, please.
Okay, so thank you. Yeah, the idea now is I would like to do a more calmly paced tutorial, hands-on with some code, just to show you what we can do and what is the modus operandi when we try to tackle those problems as physicists using neural networks. But before I do that, I just wanted to throw at you a few last ideas and especially some open problems and challenges in the field, in the domain. It's a very young field because all this story of using neural networks started in 2018. So it's really recent. So there is a lot to do. And maybe mathematicians can help us because you can prove that we can converge to the solution, because we don't, but at least you can say we can converge. Okay, so yeah, but I would like a proof that I can as an answer to the referee. So then, okay, so well, in the end, I would like to write for the 20th time this equation, right? Right? This is our starting point. We are compressing, we are representing our representing our quantum state with a neural network. Okay? Now, I can do that. And in the first paper that was published in the field by Giuseppe a few years ago, in 2018, what he did was, well, let's say the most simple form of a neural network that we physicists understand, a restricted Boltzmann machine. Let's shove it in here and see what happens. And oh, it works. The problem is that we are physicists and we know something about our systems. So for example, we know that very often our Hamiltonian is, let's say, for example, it's left invariant by some transformations. Okay, so some of those transformations that leave invariant my Hamiltonian are things like translations. Imagine you have a system defined on a periodic chain. Okay, this is site 1, this is site 2, site 3, blah blah, site 10. Now, if my translation operator, essentially, if what it does is it maps this system into one where I shift by certain number of positions my sites, you can clearly see that if the Hamiltonian is homogeneous, if the system is homogeneous, then the Hamiltonian is exactly identical. Okay, and this means it's very easy to prove that if the Hamiltonian is invariant under transformations, then also the ground state has to be invariant. Okay, so essentially we know already that psi, let's say, ground state must be equivalent, must be identical to the transformed state for any G. So G is essentially one of those translation vectors. Okay, so for example, in a one-dimensional systems with n sides and periodic boundary conditions, this means that I have at least n symmetries, right? Because I can translate by 1, I can translate by 2, up to n. We call this property invariance. Okay, and then if you were looking at higher excited states, so if you were looking at not the lowest lying eigenstate, but higher ones, you can show that those are not invariant; those are actually equivariant. So they pick up a phase depending on the G. But I will not discuss this. Anyway, the point is this for now. if we are looking for a ground state, we already know something about it. We already know that it's translation invariant. So this means that if I'm approximating this with a neural network or any variational function, I mean, let's forget neural networks, which is just a fancy name to get funding. This means that psi theta of x1, xn must be identical to psi theta of x2, xn, comma, x1, right? And so on and so forth. How do we enforce this? Then there are other properties that we might want to insert. One of the most important ones, so we didn't discuss it today, but arises when we deal not with spins, but with fermions or bosons. You might have heard that in quantum mechanics, particles are undistinguishable, for example. Then this means that if I permute any, and this is true for bosons, then it means that if I permute any couple of those numbers, then the result must be the same. Or for example, for fermions, another kind of particles, essentially all electrons, which essentially are the particles that we want to study in the end, because it's what it's where we can have an impact, where we can actually study concrete problems that are extremely interesting for technological applications, like superconductors, conductors, molecules are full of electrons. So if I want to study a fermionic system, I will have my wave function again that is defined, that takes as input the position of my electrons. And this should be identical to this object. Let's say so this very ugly notation means you can take a permutation of all the numbers here, and depending on how many elements you permuted, you pick up a -1 to that number. So if you permute only one couple of elements, you get a -1 sign. If instead you permuted twice, then you don't get anything, okay? So it means that the function must be antisymmetric under permutations. And fermions, for a series of reasons, we know that physical reason, they must be antisymmetric. So we will want to pick up a variational parameterization of our wave function that is antisymmetric. And again, this is not easy. We have some ways, they are fairly complicated to enforce this, but we need to do this. Otherwise, we will require a lot of parameters, and we will have to train our parameters. We will have to optimize them to learn this thing that we already know about. We want to insert it as the knowledge in our model. So talking about antisymmetry is hard, so I prefer not to do it, but I would like just to talk for a moment about symmetry, translational symmetries. How do we do that in practice? So the neural networks we work with, let's consider just a dense layer and one nonlinearity, right? So let's consider our log psi theta, because I remember you that we work with a log psi. We parameterize the log psi. So I have this object, and I define it to be sum over, I don't know, j from 1 to alpha n. Alpha is some density of parameters of phi of which is a nonlinearity w j I xi plus bi, and repeated indices means it's contracted or summed upon. Okay, so how do I make this object invariant under translations? So if I remap x1 into x2, x2 into x3, and xn into x1. Well, there are essentially two approaches to do that. You can either say, well, I will define my psi theta of x1, xn to be the sum over all g, okay, from 1 to n in one dimension, of exp log theta psi of tg x1 xn. Does it make sense? So essentially, I will, every time I want to evaluate my neural network or variational function, I will evaluate it n times, or number of symmetries times, and I sum the output. It's fairly expensive. And I didn't reduce in any way the number of parameters that I have. There is another approach where at the time when we found out about it, we said, this is smart. And we said, instead of symmetrizing the wave function itself, we symmetrize the logarithm of a wave function. And so we do sum over j equal 1 alpha n phi of, how did we do that? Sum over j I sum over g from 1 to n of w j I tg xi. So if you want, we can write it as xi plus g plus bi. No, sorry. The opposite. Sum over g of this. So we symmetrize the dense layer via affine transformation. In a sense, what we are doing, we are making this a convolution, okay? But where the kernel of the convolution is not a very short-range kernel, as what you usually do in machine learning, but we take a convolution which has a kernel that is as large as the system itself, and and the padding condition is periodic. So an interesting open challenge, for example, is that we try to use this, and the advantage is that since this is an high convolution, it has fewer free parameters. So instead of W being a matrix, which is n sides times alpha n, now this is only alpha n free parameters, and also B has fewer effective parameters. And one of the open questions that we have is that empirically we find that this approach works, but it's very stiff, it's very hard to train. And in practice, this other approach works much better. And we are able to get extremely high accuracy and precision with this approach. And there has been, for example, very little studies on why that is the case. A paper came out 3 days ago, I still have to read it. But I investigated numerically. For the first time, they did an actual comparison, more than me just saying empirically we find that. They actually wrote a paper about this empirical evidence, but we are still not sure why this doesn't work so well. Sorry, this works well, but this one doesn't. But still, at least we know that if we use these kind of symmetrized models, we are guaranteed, at least we have more guarantees of finding the right minima, because since we are optimizing the energy, well, we know that the lower the energy, the better is the solution, but sometimes we find that the solution we are finding, it's not symmetric. It doesn't respect the symmetries of a problem. Instead, in this case, we are enforcing them, and this is usually useful when we want to query over observables, over properties of a state we find.
Sorry, may I ask a
Yes.
clarification? No, before.
The letter is eta, ij, wij, before the... Thank you. What
Sorry?
is? The
Here?
letter, no, before.
Here?
The first letter.
W.
W, okay.
Sorry.
Thanks.
I mean, it's the W matrix now, the weights in a dense layer.
And I guess it's BJ, right?
Yes. Sorry. Yeah.
And so my question was, when you train these, so the loss is
the same,
but is using so in the first case, I say, you use psi theta. So the non-permuted one for the loss,
I'm
or
just
you
talking
use the
about
permuted one?
I'm just talking about the model.
Yeah, but you know the model, because
so you can either, essentially what I'm saying, you can either symmetrize the wave function or you can symmetrize the log wave function.
Yeah, so in the model you use the log wave function. So sorry, you
Yes.
use the symmetrized wave function every time, right?
In the loss, yes. No, in the loss we have a wave function, but our neural network architecture encodes the logarithm of a wave function.
Yeah.
So if you want, the first approach is in a sense changing the loss. The second approach is changing the model to be symmetric.
Okay. So the model, so you train still the non-symmetric one in the first case.
Here, yes, we
you train the non-symmetric one,
Oh,
but
yes.
using the loss on the symmetrized version.
Yes.
Okay, thank you.
And but then also when we compute observables or anything else, we always use this one. We change all our formulas above. It probably works better because also has more parameters. Like you didn't reduce the number of parameters. There are some arguments that we know about the fact that here you can build interference because you're combining different wave functions. Instead, in the first case, you're not. Yes, but anyway, so yeah, this is one thing I wanted to mention. What? Yeah.
Sorry, but yeah, actually, let me, when you said it, I had like the feeling. I mean, I don't want to solve this problem here in 30 seconds, of course, but like the number of parameters is like hugely different, like really.
Yes, but even if you take the second approach, which has fewer, no, you reduce the number of parameters by number of symmetries, so by n for one-dimensional systems.
By n, so it's 1/n the number of parameters.
Yes, and in general, so again, we never did any systematic studies of this, but my intuition is that even if you increase by n the feature density in the second approach, you will not get the precisions we get in the first one.
Okay. Because when you said like around like 100 particles, like it's like 2 orders of magnitude less.
Okay, this stuff, I mean, when we try to understand how they work, we try with, I don't know, 20, 30 particles to see what happens. And yeah, so when Giuseppe said a few days ago that the state-of-the-art results with neural network quantum state, blah, blah, they achieved it with the first technique in a particular system by inserting this symmetry in that way and the anti-symmetry. So in the permutational anti-symmetry, because they were working on fermions.
Have you, if I can ask another question, like, have you tried like to do the, let's say, classical data augmentation technique where you simply enlarge the data set saying that everything is like equivalent?
This is to an extent equivalent to doing data augmentation. So you sample, you do Markov chain Monte Carlo sampling, and then you augment your set of samples by all the possible physical translations.
Yeah, exactly.
It's exactly the same.
Okay, it's the same. Okay.
But I mean, it's data augmentation where you respect the symmetries.
Yeah,
exactly,
sure.
not approximately. It's not that you. I mean, you cannot do this if you have a continuous group. This only works with a discrete symmetry group.
Okay.
Because with a continuous, I mean, you can't possibly do it, or maybe you could generalize it.
Okay, but why are you saying that you also have to sample with the market? Like I would have done basically the same output, so the same energy somehow, but changing my x accordingly to the symmetry. Like why do you need to resample again? Maybe I'm not getting
No, because so we are computing the energy, right? And then the gradient of this object, which for us in expectation value of x, say theta square of E log x, right?
Yeah.
So the samples x from psi theta, if psi theta is not normalized, we have to do Markov chain sampling or any kind of sampling to get a set of x's, right? Because we would need exponentially many x's. We just want to have polynomially many. So we do sampling here. We get a set of samples x. Okay. And then we augment it by
applying the
having
symmetry.
x, then t1 x,
Exactly,
then
exactly,
t2 x,
Exactly.
etc. Since E-log is a linear function no, it's not linear, sorry. But you can show that it's linear in psi theta in this object. You can show that if you do this augmentation, it's equivalent to effectively redefining E-log to sum on all the possible translations.
It's equivalent, like defining the log on the sum. Okay, like, so
if you define E-log of x to be x h psi theta, x psi theta, okay.
Yeah.
If you now do the data augmentation, this would be equivalent to saying sum over G of TGX H psi theta TGX psi theta, right?
But you want to implement the symmetry, right? So this must be exactly as applying, because the neural network, if I remember correctly, goes from the space of X to and it outputs psi, right?
Yes.
So if you permute the X, it needs to output basically the same, I mean, the same energy somehow, right? So you mean that this, oh, okay, maybe I see now, because you can remove the T, so this is the sum.
Yes.
And so, okay.
However, we can use this trick of summing over G, or essentially redefining psi of X to be sum over G of TG X psi theta, which was approach 1. So, which is equivalent to doing this data augmentation in a sense. So we can only do that if the size of this group G is polynomial, right? Now, so we can do it for translations because they are usually n and square, I don't know. But for the permutational symmetry, I mean, it would be amazing if we could do it, but it's n factorial, so
I see the
can't.
problem.
And so we have to devise neural network architectures that are anti-symmetric with respect to permutation. And we can, but we lose expressivity, and this is still a very open field of research. So there are a few techniques, but I'm sure eventually we will find something that it will be better.
Okay, thanks.
Okay, and then the last thing I wanted to mention is that, so this is one open problem if you want. The second open problem is dynamics. So we mainly talked about finding the ground state. And yesterday I mentioned very briefly, essentially, that we can solve this equation of motion, right? Minus h psi, and this imaginary time evolution converges to the ground state. And I had remapped this into this differential equation with the objects that we discussed yesterday. And then I said, but you can actually just add an I here. And then you get, sorry, and here you have a dt. And then you get d theta dt equal minus I dt s minus 1 f. Okay. And I said, without doing any calculation, just very hand waving, that this converges to the ground state, and this converges to this gives you the time dynamics, the Schrödinger dynamics of your system. Now, solving this equation in practice, it's very hard, but we would like to do the dynamics, because to know essentially response functions, so what happens not when your system is at rest, but when you shoot a laser at it. If you want to know transport properties, of your material, you usually need to compute some functionals of dynamics. So you need to usually you take the ground state, you add the perturbation, you look how this perturbation evolves. To do this, you need to do dynamics. So the best way we have to do dynamics is with this time-dependent variational principle, and it breaks down at some point. So we would love to have more inaccurate characterization of this equation, for example. And then, yeah, and so this is another open problem. Another open problem is the sampling. So we can always sample. Sampling is nice, right? We have to do this Markov chain sampling, but this is not always what we want to do, because in some limits we have some systems where we need really a lot of samples. So we don't want to do Markov chain sampling, because I mean, in general we can do it well, but there are some special circumstances where it's a bit tricky. Or we just want to speed up our algorithms. We want to have samples that are distributed according to the correct distribution with no correlations, so no Markov chain sampling. And for those models, what we do is we use autoregressive. So for those problems, we use autoregressive models. So instead of parameterizing pi theta of x1, xn, we parameterize with some neural network this object, pi theta 1 of x1 times pi theta 2 of x2 given x1 times pi theta n of xn given xn minus 1 x1. Okay. Now this object is just a chain of conditional probabilities. This gives you still a pi of x1 xn, but it can be sampled exactly with a polynomial cost, because the problem arises from the fact that we cannot compute the normalization, right, of a distribution. If my pi theta is not normalized, I would have to normalize it to be able to sample it exactly. So I would have to sum over all the possible configurations, which are 2 to the n. Instead, in this case, to sample from pi theta 1, I just need to compute this value for 2 configurations. So I can normalize this one with a very low cost, like order 2. And then once I know x1, I can plug it in here, and I can normalize this object for the 2 possible values of x2. And I do this recursively. And so the cost will be 2 times n. Okay. Of course, to use this kind of structure, you will need to encode a certain ordering in your system. So in one-dimensional systems, this is, let's say, natural in a sense. But in 2-dimensional systems, you start to introduce some fictitious ordering that has no physical interpretation. Moreover, if you want to do this, it becomes complicated to enforce translational symmetries, because you are breaking the symmetry in your system, because your model now has an explicit ordering. So some questions that we ask ourselves sometimes is how to use this kind of autoregressive models in conjunctions with symmetries. There are other kind of models that we can use. For example, we can use flow models. Those we can sample directly without enforcing an order, but this is a story for another day. And then, okay, the last thing before I move on to the notebooks, another very big open question, let's say in this neural network approach to physics, is how to study more complicated systems. So to children in second year of physics bachelor, we teach that the world is this ideal world of wave function evolving unperturbed according to the Schrödinger's equation. But this is not the case in general. So researchers have been trying to build boxes and seal them and put qubits inside and pray to whatever higher entity they believe in, that the environment, that whatever is outside the box doesn't get in. But this is impossible, because you would need to cool it down, you need to shield it, and you can never shield anything perfectly. Also because if you want to control whatever is inside, you need to bring down something. But then it's hard to tell nature, yeah, like those electrons, please let them in, but not those other electrons. So what happens in practice is that the ideal description of quantum mechanics of this Schrödinger evolution, let's say, is not the best model of our experimental reality. So you can think for a moment that if our space were, if our universe is a huge Hilbert space of a huge wave function that describes everything, this is a composed system made up of your system, of the space where your system lives. Maybe your qubit is just a two-level system or something a bit more complicated. Tensor, the environment, essentially everything else. Experimental apparatus, the experimentalist, Jupiter, whatever else. Okay, so then, in a sense, what we want to do is we have a wave function that describes the state of the universe. This evolves indeed according to the Schrödinger equation. But then I want to trace away everything that is not my system. So in a sense, I want to go from this object to this object. Okay? So I want to go from a pure state description of a wave function of a ket to a mixed density matrix, to a mixed state, okay? Where there is both a component of quantumness and a component of classical mixedness, because this is essentially a collection of quantum states. And to each of those quantum states, you associate a classical probability. And without getting into the details of it, if you get a density matrix, this will evolve according to a slightly different equation. So it will evolve to a different equation, essentially commutator of Hamiltonian with rho, which is kinda the Schrödinger equation for a mixed state, plus some terms that tell you essentially how the environment, how everything else is acting onto your density matrix, onto your mixed state. Okay, and this is called the master equation. This is one form. There are many different ones depending on the approximation you use. But now, one very interesting problem is remapping all the utilities that we developed for pure states to mixed states. And this is hard because many of the properties we have in pure states, they are not valid anymore here. So for example, this equation is not unitary anymore. It has a very well-defined arrow of time, and it defines essentially a contracting semigroup. So many tricks you can pull off for Schrödinger dynamics, you cannot pull it off in this case. Rho is a very complicated object because it is now, you want it to be positive semi-definite, because if you want, those probabilities must be positive, otherwise you cannot interpret them as probabilities. And therefore, we would like to develop a density matrix neural network or variational approximations that are positive definites, which we have some, but it would be nice to have more of them. And then again, this equation is much more complicated to study. And so this is another frontier, let's say, in the field, which is trying to use to generalize all the utilities we have to non-equilibrium, we call it, to mixed states. And I worked personally a bit on this problem, but it's very hard. And there are many open questions. So for example, what should we sample from? So you know that for matrices, you have many different norms. Like you have the L2 norm, you have a trace norm, you have a spectral norm. Which one do you use it when you sample from rho? How to define a variational principle for mixed states? There are everything is less well defined. And maybe that's exactly why we need more people to get into these particular questions, because there are many more things to explore, and we don't know yet which one is the best. What is the best variational principle we can come up with? So, and then again, integrating symmetries into mixed states, it's another open problem. A few people have tried to do it. There are many challenges. So, and then finally, like, since you're mathematicians, what we would like in general is to have a better understanding of what ingredients we need when we use this approach. So it might seem stupid, but we would like to know more realistically what quantum states we can represent with certain neural networks. Right now, we have several proofs that tells us that neural network quantum states can approximate efficiently ground states of certain Hamiltonians in one dimension. We have very few proofs for whether we can approximate the ground states of two-dimensional Hamiltonians. We have empirical proofs, but no theoretical proofs. For example, can an RBM efficiently represent the ground state of a 2D Hamiltonian? Well, in some cases we know we can, but very limited ones. We would like to know about convolutional neural networks, about autoregressive neural networks. Can those represent efficiently the ground state of those states? And then the harder question is, can we also represent the dynamics? Because if I show that I can encode the ground state, I said nothing about all the states that I encountered during the time evolution. Can I represent those or not? Is it, do we have hope of using neural network quantum states to do the dynamics? Or the fact that it doesn't work very well and we struggle to make this work well is linked to the fact that we are hopeless, that we cannot solve that optimization problem. So yeah, so this would be, I mean, with that I would like to conclude the part on the blackboard. Posso passare al computer, per favore?
How do you do this trace out of the world? So do you learn that part of the dynamics?
No, ma va benissimo. Però si può tirare giù il... yeah, so you need approximations.
Okay.
I mean, I was
so
just
a
trying to
model of
flash
the
it.
error or something like that? Or...
So you make a lot of assumptions on how the Hamiltonian gives you what is the form of the interacting terms between the system and the environment. So usually you say, I don't know, there is a tight binding or a kind of hopping. So either an excitation can flow out of the system or it can flow in with a certain rate. And then you can, by doing some approximations on the environment. So usually you say, well, the environment is huge. So even if an excitation flows into the environment, then it doesn't really change the state of the environment. And you can make more strong assumptions, which is like, we start from a configuration that where the two states are separable. So there is no quantum entanglement at the beginning between them. And then you can go even further. You can say, well, the environment is Markovian because the timescales of the environment are much faster. Like an excitation will decay much faster than the system, than the rate of interaction between the system and the environment. And I mean, you can add approximation after approximation until you get an equation that looks like this as the Markovian approximation in particular, but you can add more. And the fewer approximations you make, the more complicated is the equation that you get. So Markovian buff is a very strong one. You get nice equations. If you don't assume a Markovian buff for environment, then you will have to keep a memory kernel, something that you will have to store in the memory what happened in the past, how the system interacted with the environment. And for this is called non-Markovian open quantum systems. There are extremely few numerical methods, and they can simulate only a bunch of particles, I think 4 or 5, for very short times. So that's a field that if you have someone comes up with a new algorithm to do these kind of problems, it's very interesting. And it's also interesting because the problem of non-Markovian bus, it's also strongly linked to some open questions in strongly interacting electrons. So So the problems we started from, if you want to describe a system with thousands of electrons, there are some theories that allow you to remap this to a problem of non-Markovian open systems. And so if you can solve one problem, you can also have an impact in the other domain. So let's say non-Markovianity, it's a very big question in physics that people avoid it because it's complicated. But if you can tackle it efficiently, you can have a huge impact also in other fields. Okay, to conclude this, I wanted to let's say, yeah, to showcase a few of the things of yesterday. By the way, if you want to play out with the things I'm showing, there is this beautiful website called netcat.org, which is a website of our software. And if you go on documentation, you have a series of tutorials here, like the one I was showing you yesterday and a bunch of others. And you can run them on Colab and whatever. And also, if you go on, not here, if you go on my GitHub, well, if you go on my GitHub, there is another repository, lectures, where I collect all the lectures, all the notes, and there's a bunch of notebooks here. One about an introduction to Jackson automatic differentiation that we didn't do. One about neural quantum states, and one about doing dynamics with neural quantum states. We didn't go through them in detail, but there's a bit more things than you find on the main Netcat website. And if you're interested, you can play around with that. Especially if you're interested with Markov chain Monte Carlo sampling, convergence rates. This is discussed in the second notebook. So I wanted to pick off where I was yesterday. So again, if you remember, we had defined the Hilbert space. So this is this object that allows us to query to get some of those X's, some of those bit strings that we use as basis of our space. So we had constructed the Hamiltonian with this sparse representation. We had used the exact diagonalization to compute the ground state energy. And then we had used this amazing, super powerful one parameter variational ansatz to get an approximation of our ground states. And it didn't really work because, I mean, it wasn't terrible, but it was not very nice. One thing that I would like to underline is, and we were pretty much here. So one thing I wanted to underline is what happens when we are using those encodings. So, okay, now it will take a moment to run because it's diagonalizing a big Hamiltonian. Yes. So for relatively small systems like this one, we can actually generate and keep in memory all the basis elements, right? So all X in this case would be, a tensor with 1 million elements because we have an Hilbert space of dimension 1 million. And the second dimension is 20 because we have a 20 side. So it's this bit string of 20, -1, and +1. Okay. So now if I feed this to my neural network ansatz, right? What I would expect is that how did I call it? MF model. So what I expect here is that, sorry, variables. So what I should expect now is essentially that I should be getting 1 million real numbers, right? And those will be real numbers because we took our model to be real. So we are encoding the logarithm of a wave function to be a real number. But since we are encoding the logarithm of a wave function, this means that the wave function is the exponential of this, right? So the wave function is going to be positive coefficients. for this particular problem that we are looking, this is correct. We know it already. So transverse sterilizing model is, in physics, we say it's stochastic, which means the ground state is all positive. But in the general case, you will want to use complex numbers or add the plus minus I pi, such that the exponential will be something with a sign or something with a phase, right? So essentially what you can, if you want to construct the wave function, then you will have to take the exponential of this vector. Does it make sense? Now, since the ansatz we are using is this mean field ansatz, I think that we are lucky enough and this will be normalized. But I'm not sure. Yes, this is normalized. But in the general case, you might need to normalize this object if you work with it. Okay, and so with netcat, we can compute the expectation value very easily, right? You just call variational state, so which was this black box I said, this MC state, Monte Carlo state, which just does everything for you, and you pass it your Hamiltonian, and it works, and it computes a bunch of stuff. But I would like to show you that, I mean, this is not just magic. What is going on under the hood is that essentially we collect a set of samples, right? So it's doing this state.samples. And then for every one of those samples, we want to compute the ELOC, okay? So the ELOC is what? It was sum over the ELOC of x was x h psi divided by x psi. Alternatively, sum over x prime of h x x prime psi of x prime divided by psi of x. But since we are encoding the logarithm of a wave function, this means that this is sum over x prime, h x x prime, exponential of log psi x prime minus log psi of x. Right? So if we want to compute those terms, we just have to implement this, okay? And the way you do that is very simple. You simply take your Hamiltonian, this sparse Hamiltonian, and we want to do the sum only on the non-zero entries. So we have a function in this case called getCon padded, to which if you pass him the bit strings x, it will give you the x prime for which there is a non-zero matrix element. Let's call this x maybe. And of course, it also gives you the matrix elements. Okay, so if you want those x's that we label with bit strings are nothing other than numbers saying the first row, second row, fourth row, etc. So they're indices that we are storing as those bit strings because it's more efficient for us. Okay, so x prime is now. So maybe let's show this. So x is a tensor 125 by 8 by 20. This is because, well, we have bit strings of 20 spins. We have 8 Markov chains, and the Markov chains were 125 long each. This is because by default we use those numbers, but you can, of course, you can ask more samples, more Markov chains, just one Markov chain, whatever. And so the connected elements will be, well, there are 21 connected elements for every sample. If you remember, it's because we in our Hamiltonian, we have this sum over all the sides, and we flip one spin at a time, plus the diagonal term that is sigma z, sigma z. So the connected terms are n plus 1. And so this is doing exactly that. So we have 125 by 8 by 21 by n plus 1 connected elements. And the last object that we have are the matrix elements, right? And so those are 125 by 8 by 21 values of h x prime. Does it make sense? Okay. So now that we have those objects, we want to compute, if you want, what is between the square brackets. So I will do mean field model dot apply, which is just the way to call it. I will pass in the variables that I store in my variational state and the x prime. And these will give us 125 by 8 by 21 real numbers, which is log psi of x prime. And then I can simply subtract the same thing for x. I think this will, it will complain now because Python is not very nice. And yes, and what is going on here is that here I have 125 by 8 by 21, and instead this object is, and instead the second one is 125 by 8. So, I mean, this is the usual super boring things of coding up those algorithms. You have to make Python happy about shapes. So we will have to reshape this to be 125 by 8 by 1, so that he knows that the last dimension can be broadcasted. Now he's happy. So we can take the exponential. Okay, so this is the last line. Shape. So this should be again 125 by 8 by 21, and it's the difference between those two numbers. And I have to multiply it by the matrix elements, so by h x prime. And finally, take the sum over the last axis, meaning over the x prime, because I'm storing the x prime dimension, the connected elements dimension, I'm storing it on the last axis. Does it make sense? Yes?
So what I like the which is the difference between like the J and P and the NP? Like you are why are you storing them as a JAX object? Like or if you do this, like can you also access them like naturally, like using NumPy, or there is like huge difference?
You could. I don't know if I imported it now. Yeah, I didn't, but
okay, so they're the same.
Wait, but so I would tell you, go through the notebook 1.
Okay.
And learn a few things about JAX.
Okay.
In very few words. So as long as you write code like that, it's fine. You can switch from one to the other. But you have to. You can think of, if you keep a JAX an array as a JAX array, JAX can do some magic on it. So if you write a function, okay, so I could write a function, compute elogs, okay, and I pass to it samples, okay, and x prime and matrix elements, okay. I put all this stuff in a function with JAX NumPy, okay.
Okay.
JAX NumPy is almost like 99.99% equivalent to NumPy, but has a few extra features, let's say. So if I do this, I can do compute elogs x prime mels, okay, and this runs, okay. So now, if you only use JAX.numpy, what happens is that JAX knows how to trace this function, and so you can JIT it.
I see.
Meaning that essentially what you will do is it will do this very fancy thing. Let me see. No, let's do. So if you run it, so make JAX PR means that JAX essentially will now run your function with mock data. Okay, so it will feed your function. some empty boxes. You can think as a JAX array as a box where on the surface it says I have floating point numbers and my shape is this one inside, but inside there might be or might not be something, okay? So when you want to compile your code, if you want, when you JIT it, the first time you run the function, what JAX does is it passes to your function those empty boxes, okay? And JAX.numpy functions, they know that if they get an empty box, they should just return an empty box with the correct shape. So if you multiply a matrix vector with certain shapes and certain types, you know that if you multiply a float by a complex, you get a complex, etc. But it's still empty, okay? And when it does all of these, and when it gets to the end, and actually inside of the boxes, they are storing all the instruction they did, like they're annotating. So in a sense, it's building up a representation of your code, but that it knows how to work with, okay? And this make JAX-Pierre is doing exactly that. He's feeding empty boxes to it, and you see he's recording all the informations that we have. So here you see it says there are 4 inputs. So A is a scalar floating point number. I don't know why he's dreaming that up, but B is 125 by 8 by 20 floating point number, which is our X. C is 125, 8, 21, 20, okay? And then you can see here it does multiplications. I don't know, you can find stuff.
Basically it recompiles it somehow.
So first it uses this tracing mechanism to build a representation of your code. This fancy stuff, because now it knows how to operate on this stuff, okay? And then it will compile this. Okay. Tracing is just to get the code that JAX knows how to work with, and then he compiles this. And the nice thing is that since he has this very nice structure, he can now run many optimization passes on it. You can also tell him vectorize this function. So if I pass him objects that have an extra dimension, so imagine your code is doing a dot product between 2 vectors, okay? Or yes, a dot product between 2 vectors. And now he builds this function up, okay? And now you want to run it for many vectors, okay? He knows how to replace every operation with a vectorized one. So you will replace vector dot products with matrix vector products and things like that. Cool, and he can do it because he has this representation.
Very cool. Okay, so it will run parallel on the registers.
And gradients, or better, push forward and pullbacks. Well, he knows for every one of those operations how to do the pullback and the push forward.
Cool.
And this is why it's one way to generate code. However, if you now were to put NumPy inside of this, okay, what happens is that it will crash. And the reason is that NumPy doesn't know what to do with an empty box. Okay. And it works as long as you're not using those functional transformations that JAX gives you. But if you want to use JAX-JIT, JAX-grad, etc., you need to use the JAX functions because they know how to work with those empty boxes.
Have you ever tried using Numba or something like that? Do you advise that it's bad? Because I just a little bit of experience with Numba, and it looks similar. Do you think that this is better? I'm sure you do.
It depends what you want to do. So JAX is very limited for not very limited, but it's less
flexible.
So I will give you an example, but then I will go back to physics, which is this. For I in ln x, okay, let's say v equals 0. For I in ln x, v equal v plus xi, okay, return v. So this is the sum, okay? Sorry?
Range ln x?
Sorry, thanks, yes. Okay?
Yeah.
So what happens? Let's build the x, which is GNP arrange 10. Okay. So what do you think will happen now? So first we initialize v to 0. It's fine. Then we take the length of x.
Yeah.
Well, length, we look at the surface of a box, says, oh, this object has length 10, so it's fine. And it will start looping, okay? And then now here you say xi, the ith element of x. Okay, so JAX is smart. So when you ask him the ith element of a vector, it will give you a smaller empty box that says what is inside this empty box actually comes from that over empty box. So this you can do.
Like a pointer, somehow.
Yes.
Okay.
It's kinda, yes. But he will not know. Let me do this. But this pointer has no number inside. So I will make you an example. With some xv. Okay, so if I run this code now, no, sorry. You see, he's printing this at every iteration. You see traced, shaped array. This is essentially the surface of a box, saying this is a scalar in 64 brackets means scalar. There is nothing inside. Okay, so you can always index inside stuff, but as long as you use them with other JAX functions, it's fine because it's just building up this trace representation or tape. If you print them, they look like nothing. But what is happening inside of this function, okay, in practice? So this loop, so inside of the tape, is recording the operation v equal v plus xi 10 times, okay? So you see our code takes an input, which is 10 integers. And now at every iteration is saying dynamic slice means index, okay? So index into C, which is our array at the 0th point, then index at the first, second, etc. And then it's saying add to 0 E, which is the output of the indexing, and then add F to H, and okay. So there are 10 operations here, and then if you compile it, I mean, this is how you would write it in C in a sense.
Yeah, exactly.
But this is super bad because the JAX compiler is not optimized to do this kind of operations. It's not a C compiler. What he would prefer to have is this.
I see.
Okay, because someone implemented already in JAX some elementary operations like sum of arrays, and this is very efficient. So to say that if you can write your algorithm like NumPy style, let's say with high-level functions, then all is great. And JAX is very fast. And the nice thing of JAX is it allows you to compute gradients, to run your code on GPUs without changing any line. At the same time, if you cannot write your algorithm in that way, or if for example, you want to do something like where you create a vector with random shapes, with dynamical shapes, this you kinda can, but it's much more tricky, and maybe performance is not good.
I see.
So it's really for machine learning kind of workflows where you have static shapes, you have PyTorch is a bit does this when it can, and when it can't, it doesn't error. It just falls back to very low performance stuff. But most machine learning compilers do these things.
Okay. Yeah. Okay. Thank you.
And to conclude, I forgot. Okay. Anyway, this. So in general, yes, and the last thing, so you can also do for loops that JAX knows how to handle efficiently. It's how you write ODE solvers, because then, or if else, that someone had asked the other day, you can use there is a special function which is JAX lax condition, which is a way for JAX to know how to work with a condition with an if else statement. But again, yeah, it gets annoying to work with them. So as much as you can avoid it, anyway. So we were implementing our function. Now I deleted my code, but you've seen that we can compute the elogs, and then you can just do the average. Okay. So in general, the idea of Netcat and many other packages that exist is just to hide away all the details of working with these objects. Blah, blah, blah. Yes, so one thing I wanted to discuss very briefly is this. No, let's go on. Yes. And yesterday I had shown that, right, we can write this optimization loop by hand where we compute the energy, the gradient by running expectant gradient. We can store the energy, etc., etc. So the important thing, and this is fairly important, is that if we look at the parameters of our model, this is now a restricted Boltzmann machine. So I have 3 sets of parameters. I have a dense layer with the biases. I have the kernel, so the W matrix when I write it on the blackboard. And then I have the visible bias, which is an extra bias in the first layer. Okay, so if you notice, those parameters are stored in a set of nested dictionaries, right? So if I compute the gradient of the energy of my model, the gradient must have the same structure as my original parameters. So if my original parameters are stored as a dictionary of, as a set of nested dictionaries of arrays, I want my gradient to have the same structure, right? Because then I will want to be able to take my parameters, add the gradient to it, and get the new parameters, right? So while you can work with arrays and with functions, you could concatenate all your parameters together and have a huge array. In machine learning, it's very common, if you did it already, to store the parameters as a dictionary of arrays. And then if you want, we use this function, juxt.trimap, which takes a certain number of inputs and then executes this function on the corresponding elements. Okay, so if you want, if I have A, which is 1, and B, which is 2, and A, which is 10, and B, which is 20. Sorry, and the function is xi plus y. Okay, so this is essentially taking every element of the first set, every element of the second set, and when they correspond, it applies this function. Okay, so you see, I get this. And so for the gradient, we do exactly the same thing. It's this line here. We take the parameters, we take the gradient, and we do x minus 0.05 y. And this was what this code was doing. Right? And then if we plot these, we see that the energy is not amazing. Okay, this it's not very important. It's about Netcat being very fancy and doing coffee for you and storing all the values of the energy at the intermediate steps and doing a bunch of things that are nicer, showing progress bars that tells you how much time do you have left before the, basically to sleep before the simulation is finished. And yeah, okay, and this is wrong. So let's keep this. Yes, let's keep this. Let's try this. So let's try to use a feed-forward neural network. So basically a restricted Boltzmann machine, if you want. So the way you would define it in this with Flux, so in say in JAX, would be to take, let's say, alpha equal 1. So again, if you will ever be interested in using those things, you can. There are plenty of tutorials online, but the idea is you define those classes. It must be some flux.nn.module. Just it's a way to tell him this is a neural network. You can define some parameters, let's say, that you can change. So alpha is the feature density for me. So I want that my weight matrix will be, if the input has n variables, then the output must be alpha times n. And you see here we define this call function so that when we execute it, it takes one input, x. And the first operation I do is I construct a dense layer. So nn.dense, like inside of flux.nn, you have many different layers. Let's see if I can show you. Yeah, you have batch normalization, convolution, LSTM, I mean, dense, dropouts, embed, you have all the things, RNN, I think, GRU, I mean, all the things you might like and not like. Anyway, so I build a dense layer with a certain number of features, right? So x.shape -1 means look at the last dimension of my input, where I usually encode the bit string, right? So the last dimension is the number of variables, the number of particles I have, the number of spins, and I multiply it by alpha. And this is the number of features of my dense layer, so the output size. And then I apply dense to my input, dense of x, and I get y. So in this framework, essentially you intermix the code to define what are your layers with the code that executes your layer. And then when you compile, JAX is very smart and separates the two codes. Then we apply nonlinearity, for example, RRU, and then you sum the last dimension, okay? So then we can build this model, this feed-forward neural network with alpha equal 1, for example. I can build again a Monte Carlo state. And this will automatically initialize my parameters, right? It's this stuff again, and you can compute everything you like. This is just one layer. If we wanted to add another layer, we can do this. I can add dense 2. Now, of course, I cannot use x. I need to do y.shape. No, sorry. So the input dimension is automatically inferred from your code. And for the output, let's say, for example, we could add another variable. So alpha 2, let's say. And let's say it's 1 again by default. And so here we have alpha 2 times the original one. Okay. Yeah, you can do it as you want. Yeah, let's say y. Because this is just the output density, so you can, I mean, normally you would define it. You can put any number there, essentially it will always work. So we can redefine y to be dense to y. Okay. And then we apply, sorry, I forgot. We apply the ReLU twice now. And then we sum at the end. Okay. Now, if we look at the parameters, to avoid printing too much stuff, I will do this. I would just print the shape and the D type, not everything that is inside. And so you see that our parameters now are dense 0, dense 1, and I have a bias and a kernel for both of them. And so, for example, if I change alpha 2, I put it to 2, what would happen is that the second layer has 40 outputs. Or if I do alpha, the first layer, I put 1, 2, and then I put 0.5. He complains. I think because the size should be an integer, so we have to convert it to an integer. Yeah. So now, okay. This is no longer true. Okay, so now to run the optimization using Netcat's fancy optimization loops, essentially what you need to use is an optimizer. So you can, the best thing you can do is you can import Optax, which is a package of optimizers, and you can use optax.sgd, yes, with a certain learning rate. Okay, I don't remember how they call it. optex.stgd doesn't exist. Learning rate. Yeah, it's all minuscule. Was extremely important programming problems. Okay. And then you can build this VMC, variational Monte Carlo driver, that Giuseppe loves. And essentially you feed it the Hamiltonian, of which you want to find the ground state, the optimizer, so the stochastic gradient descent we are doing right now, the variational states, and not this because I want to talk about it later. So let's rerun the optimization. So I will now I will build an optimizer, I build a new variational state, so it has initial parameters that are random. I run this optimization, okay, for 300 steps. And you can do plot of log data energy. Beautiful. Yes, so this happens sometimes. You see what happened is that we started and then the energy exploded. Huh? Yes, exactly. So if we look at the parameters of the variational state, yeah, it's hard to tell, but essentially you have fairly big numbers in the first layer, 0.4, 0.5. If you take the exponential and sum many of them, you get very big numbers. So essentially there are two possible problems. One is that our learning rate of 10 to the minus 1 is too large. The other one is that we initialize the two-layer neural network that I was forced to do with too large numbers. Okay, so the first thing I would try is to use 10 to the minus 3 as a learning rate. And you see that the energy, yeah, now is minus 22, minus 23, so it's much better. Yes. Yep. Okay, still with respect to the exact solution, we are very far, and we are using 2 layers neural network, so it's very bad. Now, the problem is that we are falling into a terrible, mischievous local minima. So if you think about what we had discussed yesterday, we have this very fancy technique of imaginary time evolution. We just need to solve this more complicated equation. So I want to show you how to do that in a second. So I will just, don't look because you get a headache. So this was my code, right? So my optimization loop. So this was my optimization loop. The first thing I was doing is I compute the energy and the gradient, right? I have to finish now. Yes, I will finish very soon. And we are storing the energy. And now, if you remember, we want to solve this system of equation s to the minus 1x to get the updates. Sorry, s to the minus 1f, and f is the gradient of the energy. So the S matrix can be built by simply calling vstate.quantum geometric tensor. Because we physicists call it like that. You get this object, QGT on the fly, which is, it's not really the quantum geometric tensor, is a box that pretends to be one. Okay, so you can convert it to a dense matrix, for example, and it has many numbers inside. If you remember, it's an object whose size was the number of parameters by number of parameters. So in this case, sorry, too dense. It's a 1660 because we have these many parameters. And the nice thing is that actually inside it stores nothing. It's just computing things when it needs. but you can use it to so I didn't get the chance to talk about it, but if you remember, the S matrix, Sij, is actually sum over K of Jik transpose J K J. Do you remember that? Do you recall that? Okay, so now how do we find, so how can you usually solve delta theta equal S to the minus 1 F for F vector? So there are two ways that I know of. One is to compute S to the minus 1, pseudo inverse, usually cubically expensive or order of. Another approach is to solve the linear system of equation S delta theta equal F. And there are many iterative optimizers like conjugate gradients, MinRes, GMRS, and I don't know, you tell me, that solve this. And the only thing that you need is to be able to compute efficiently S times X. So S applied to a vector and you get a vector out, okay? And it turns out that the whole reason that I like to talk about Jacobian vector products is because people for many years, also in standard machine learning, they didn't realize that if you want to use the Fisher information matrix, the best way to use it is not to construct this, to compute the Jacobian, to contract an inner dimension of the Jacobian, and then apply it to X. But it's actually to just write this object, okay? So you compute a Jacobian vector product, you get an object that is V tilde K if you want, and then you compute another Jacobian vector product, and then you're happy. And this is much faster. So of course, the day that we decided to write a paper about this very stupid, very trivial remark, some people from Google did that. But at least I was happy because it meant it was not going crazy. So what this does, essentially, it has a way to perform the matrix vector multiplication of the variation of a geometric tensor times a vector of parameters. And now I know that my vector of parameters is this dictionary of dictionaries of tensors. So it's not really a vector, but morally it's a vector, right? Because morally it's the vector of my parameters. And so if you do this matrix vector multiplication, you get the vector of moral parameters. Okay. So to conclude, essentially you can build this quantum geometric tensor, and then you can ask it to solve using some JAX sparse, no, JAX SciPy, sparse linalg CG. So, and we want to solve a system between S and the gradient of phi, of the energy. We get the solution dW, and now we update our parameters according to this solution, okay? And now it will crash, of course, because when you do those things live, yes, we state parameters. Why? Okay. Yes. The reason for this crash is because this also returns some infos. So the linear solve also tells you how many iterations it took and other things. Okay. So if you do this, and now every iteration is more expensive because we're actually solving a linear optimization problem. And yeah. Yes. So interestingly, so you remember that I said you can do real-time evolution or this imaginary time evolution that gives you the ground state. So so you know that solving this linear system requires a number of iterations that goes with the condition number of a matrix, right? So we often regularize this matrix by adding some diagonal shift terms so that we have that it's a bit better conditioned. But we cannot do this when we want to do the correct time evolution, the Schrödinger's dynamics, because if we add the regularization, that we are solving some over dynamics. Can only do it when we are looking for the ground state. So essentially, so you see, like now it's slowing down as time goes because the condition number is getting worse. The S matrix is getting more and more ill conditioned because as you approach the ground state, probably many eigenvalues start to it becomes more and more degenerate because we are very over parameterized in that region. So, well, just for sake of speed, I will just show you. We have to go. So we can just use the netcat thingy to run with this quantum geometric tensor. We call it SR. I will not talk about why, but okay, because in physics we call it like that. And if I run it, I think it will be worse. Yeah. Okay, so if we had more time, I would show you how to debug this and how to play with and how to get this to converge. And the answer is in the initialization of the neural network. So the parameters are it's an initialization problem, but unfortunately, I don't have the time to go through it.
Okay, thank you, Filippo. Let's thank Filippo again.
Okay, so today we resume our discussion of sampling. We're going to now like see why this one of the reasons why this gradient flow perspective on the Langevin diffusion is useful for understanding sampling. So on this side of the board here, I've recapped all of the optimization results that I talked about in the first lecture. So we said that for the continuous time gradient flow, under strong convexity, we had fast convergence to the minimizer. And then under a PL inequality, which is this gradient domination inequality, this PL inequality is implied by strong convexity, and it holds for some non-convex potentials, and implies fast convergence of the objective gap. And then we also saw how to obtain these results in discrete time. So if you discretize and then run the gradient descent algorithm. So to summarize, we had results for the continuous time gradient flow, and then we moved to discretization. To do the discretization, we need to add these additional smoothness assumptions, but then we're able to get results for the discrete time gradient descent. So what our aim will be for today is to get like all of the analogs of these results, but in the world of sampling. Okay, so the first thing to notice is that the reason why these kind of optimization proofs are extremely useful is because they apply like whenever you have an optimization problem, including in more abstract spaces. So what I told you last lecture is that Langevin diffusion is a gradient flow, just like this over here, but now this gradient flow is taking place in the space of probability measures. So now I claim, without like going through all the details again, that you can actually adapt all of the gradient flow proofs from Euclidean space to Wasserstein space, and then you'll get exactly the analogs here. So what are the analogs here? This convergence to the minimizer is going to be convergence in the Wasserstein distance, because remember that the metric that we place on the Wasserstein space is the Wasserstein distance. So that's the analog of this Euclidean metric. Okay, so if the KL divergence is strongly convex on the Wasserstein space, then you get exponentially fast convergence in Wasserstein distance. And if this KL divergence satisfies a PL inequality, then you're going to get exponentially fast convergence in the objective gap, which is the KL divergence. So you'll get that the KL divergence to pi is at most the KL divergence at the initialization times exponential of -2 alpha t. Okay, so we obtain like criteria for the Langevin diffusion to converge to its stationary distribution fast. But what I haven't told you yet is like how do we interpret what these conditions actually mean, right? So the first thing we want to do is to like find a condition for the KL divergence to be strongly convex in the Wasserstein space. That's going to be the first part, is to try to calculate the Hessian of this KL divergence. Are there any questions about what we're trying to do here?
I want to ask you to comment on something, because like from the rate of convergence side, we didn't gain anything on going from ODE to Wasserstein, right? So on the rate of convergence.
We didn't gain anything. Yeah, it should be an exact analog, right?
Exactly. So, but can you comment something like what is the advantage in general of like looking to this problem like on the space of probability measures with the Wasserstein distance?
I mean, so like this is a different problem from optimization, right? So, so I guess I'm not sure what you mean by gaining something, because we're just trying to like replicate the successes of optimization, but in a different field.
Yes, but I mean, what is the advantage of taking like this point of view of looking to the Langevin has a gradient flow of the KL divergence with respect to the Wasserstein distance, and not to do what people have been done 10 years ago?
Right. So what you're saying is like this particular result can be derived more directly. I mean, okay, so there's several reasons. One is like it gives you a new way to interpret like what the Langevin diffusion is, and then like interpret what are the conditions that will cause it to converge fast. And then also like from a algorithm design perspective, this is kind of like the fundamental intuition behind the Langevin diffusion that will help you like design new algorithms. That will maybe be discussed like next lecture. I'm not sure if I'm understanding your question. Okay. Okay, so let's calculate the Hessian of this KL divergence to see when it's actually strongly convex. Yes.
Sorry, in the square of sampling, the second orange box, it is KL of P less than or equal alpha times PL.
Yeah, this
okay.
is.
Oh.
So if the KL divergence satisfies a PL inequality in the space of probability measures, which I haven't really told you what that means yet, then like from this abstract theory of gradient flows, you immediately get this convergence result.
Okay, yeah.
So we know like that these results hold. What we have to do is find out what these assumptions actually mean.
PL stand for?
The Polyak-Logishewicz.
Okay, thanks.
Can I even spell this off the top of my head? Polyak-Logishewicz. I think. Approximately. Okay. That's why we only write it as PL. Okay. All right. Before we calculate the Hessian on Wasserstein space, let's just recall what it's like to differentiate a function on Euclidean space along a curve. So let's say like x is a curve in RD, and then I have a function f. So if we want to calculate the Hessian of f, then clearly what we should do is differentiate f along this curve twice, right? So what happens when you differentiate twice? So the first derivative will give you the gradient times the velocity of the curve. Okay, and then if I differentiate twice, and let's say I just evaluate this at time t equals 0, then what do I get? I actually get two terms. So the first term is the Hessian that I want. evaluated at like the velocity of the curve. But I also get a second term from the chain rule, which is the gradient of f, and then the second derivative of the curve, the acceleration of the curve. Okay. So this tells me if I'm interested in the Hessian of f, then the second term is kind of an annoyance to me. I want it to be 0. So what that tells me is I should really differentiate the f along curves which have 0 acceleration. Right. So this tells me I should look at geodesics. Because for Euclidean geodesic, the acceleration will vanish, and then the second derivative of f will really give me just the Hessian term. Okay, so that's why when we differentiate this Hessian in Wasserstein space, we're going to also need to look at Wasserstein geodesics. So let's recall the KL divergence is the sum of the potential energy plus the entropy plus the constant. We're not going to care about the constant. So we're going to do the same thing where we look at these two terms separately. This is the potential energy, this is the entropy. And then we're going to look at the W2 geodesic, which is a curve of measures. And what does it mean for this to be a geodesic? Well, if T is the optimal transport map, from mu0 to mu1, what we said is that the Wasserstein geodesic has an explicit form. You linearly interpolate this transport map with the identity map, and then you push forward the initial measure. And we're going to refer to this interpolated map as T sub little t. Okay, so recall this is what the structure of Wasserstein geodesics looks like. We have measure mu0, mu1, and then if we look at what is the tangent vector to this geodesic at time 0, the tangent vector is the transport map minus the identity. Okay. So quick quiz, along this Wasserstein geodesic, what is the tangent vector at some other time, v sub t? Is this also equal to transport map minus identity? What is like the tangent vector to this geodesic at some intermediate time t? Is the tangent vector also equal to capital T minus identity? So I did tell you that along Wasserstein geodesics, particles travel at constant speed, right?
Yeah, I mean, if this is a geodesic and there is no acceleration, I'd say yes.
Okay, so the tangent vector to this curve is actually T minus identity composed with T sub T inverse. So maybe like it should make sense if you think about it a little bit, because what you have to do is you have to like pull back the particles to their initial position through TT inverse, and then you look at the original velocity with which they started traveling. Oops. Okay, so let's start by differentiating V twice along this geodesic. Oh, I should say, like, because this is the tangent vector at time 0, what we expect is that if we differentiate this potential energy twice and evaluate it at time 0, this should be equal to the Hessian, the Wasserstein Hessian. How should I write this? Let's say the Wasserstein Hessian of V at mu0 evaluated at v0, V0, right? Like the Hessian is a quadratic form. And then when we differentiate twice, we should get the Hessian of our functional with the velocity vector. Okay, so that's why we're going to differentiate this guy twice to find out what the Hessian is. So this one, I guess like it's probably easiest to do this calculation from the Lagrangian perspective. So remember that if xt is a particle with law mu t, then at the particle level, we're just traveling in straight lines. Okay, so if I want to differentiate this twice, this is just the second time derivative of the expectation of v evaluated at this particle xt. And because xt is traveling in a straight line, we really are just back to this Euclidean calculation. So then it's just the expectation of Hessian v times the velocity of this curve, which is t of x0 minus x0, t of x0 minus x0. Okay, so if I evaluate this at time 0, this xt just becomes x0. And then if I recall that t minus identity is v0 and compare with that expression up there, that tells me the Wasserstein Hessian of v at v0 is just, let's say, the Euclidean Hessian of this potential v applied to v0 integrated with respect to mu. Okay, so this is a pretty intuitive formula. It tells you that when you lift this potential v from a function on Euclidean space to a functional on measures, then the Hessian of this on Wasserstein space is just like the integral of the Hessians of the potential on Euclidean space. So here, really, like the Wasserstein space reflects the Euclidean space. And moreover, this tells us that properties of v on Euclidean space translate to properties of this functional on Wasserstein space. In particular, you see that the Hessian, if the Hessian of this function v is lower bounded in Euclidean space, then you get a lower bound here, which gives you like a lower bound on this functional here. So then this thing is equivalent to the Wasserstein Hessian being lower bounded. And also, if we have an upper bound on this potential in Euclidean space, then the Wasserstein Hessian is also upper bounded. Okay. Yes.
Sorry, I'm a little bit like lost, like from the, I mean, when you compute the expectation value of v at xt, right? So what's v? So v is our function, like.
Yeah. So this is our
one, right?
functional.
Okay.
Curly v of mu. It's just the integral of v with respect to mu. This is like the potential.
Okay.
Of the, yeah.
But then what's the meaning of this, like nabla square W2 v0 v0?
This is supposed to be the Wasserstein Hessian.
Yeah, but like why the square bracket with v0 v0?
So the Hessian is a quadratic form, right? It takes in two tangent vectors of the curve.
On those two. Okay. Now
yeah, and then spits out a real number. So
okay.
And because I guess like if you just want to talk about the Wasserstein Hessian, it's some kind of like tensor, I guess, on the tangent space of Wasserstein space.
Okay.
Just kind of a complicated object, so it's much easier to just evaluate it at two velocity vectors.
Okay, I see. Okay, thank you.
Yeah, so in summary, for this like potential energy, any like convexity or smoothness properties of the potential in Euclidean space immediately translate into convexity or smoothness properties on the Wasserstein space.
Good question. Do you choose the vector v0 to have norm 1, or is it the upper bound like up to a constant bounded by beta?
So this should be thought of as like an inequality between operators.
Okay. Oh, yeah. So then
Or
you
like
bring
if you're
operator
familiar
in.
with Riemannian geometry, then this thing, the Hessian is like it like eats two tangent vectors. It's an operator that takes two tangent vectors and outputs a real number. So this should be interpreted as like lower bounding alpha times the metric tensor. But in this case, the metric tensor is just the L2 norm of V0 squared.
Yeah, yeah.
Yeah.
Thank you.
All right, so let's do the entropy. So again, we have this Wasserstein geodesic, and this time I'm going to use the fact that it's the push forward by this map T sub T of mu0. And then we want to calculate the second time derivative of the entropy. Okay, so the way I'm going to do this is like a little bit slick. It's like, I guess not clear why this way of doing the computation will be the easiest way of doing it, but like for the sake of time, I'll just like try to do the fastest derivation of this. So what we want to look at is the entropy functional, which is integral of mu t log mu t. But because mu t is the push forward of mu0 by this map tt, then we can use the change of variables formula, which no one remembers, so I'll remind you. So what does the change of variables say? It says that if you push forward a density mu by a map t and you get a density nu, and let's say like this map t is invertible and nice, then it gives you a formula for the density. This density is mu of x divided by nu of t x is equal to the Jacobian determinant. Okay, so we use this change of variables formula. But the first thing is like, because mu t is a push forward, I can write this integral as a integral under mu0. But now like the integrand is pushed forward by this map T sub t. So this is just the definition of push forward. Okay, but now like I have this expression, which is exactly the denominator of the change of variables formula. So when you plug in the change of variables formula, this this density mu t composed with the map tt is just mu0 divided by the Jacobian determinant. And now this is really nice because the mu0 log mu0 is just the initial entropy. And then I get this term, which is minus the log determinant. Integrated with respect to mu0. Okay, so now once I have this expression, it's very easy to differentiate in time because the only thing that depends on time now is just this map. So I calculate the time derivative of the entropy, and I just get the time derivative of this minus log determinant.
Can I just ask, how did you get from the sort of the first inequality? Like mu t log mu t to mu naught log mu t. Yeah, this one.
And so if you have like any function phi, and then you integrate it with the push forward measure, this is the same thing as integrating phi composed with t with respect to d mu. So that's the definition of push forward. So then because mu t is the push forward of mu 0 by tt, then you get this.
Got that. Thank you.
Okay, so how do we do this computation? Actually, like you can skip the computation altogether if you just want to show that this thing is convex, because we know that minus log determinant, this is convex, a convex function on the PSD cone. And also grad tt is linear in t. Remember, like a t sub t is like a linear interpolation between your transport map and the identity. So it's just linear in t, and then I take a spatial gradient, but it's still linear in t. So this is the composition of a convex function and a linear function, so it's convex. So that immediately tells you that this entropy functional is convex on Wasserstein space. But if you like write down what is actually the second derivative of this log determinant function, then you can also get an explicit expression for what the time derivative of the second time derivative of the entropy is. It is equal to this expression. Okay, so you take the gradient of your transport map, subtract the identity matrix, because this is a matrix, and then you take the Hilbert-Schmidt norm squared integrated with respect to d mu. So this is, it turns out that this is what you get when you differentiate the log determinant. Now, one thing is, like, from this expression, it's pretty clear that this is non-negative. So that means it's convex. But the reason why I wanted to write this down is if we wanted to show smoothness, can we bound this by a multiple of the norm of the tangent vector? So the answer is no, because like in general, like you can't hope to bound, you can't hope to control the gradient of a function by the function itself. That's like the reverse of what the Sobolev inequalities tell you, right? So the conclusion from this is that this entropy is always convex, but non-smooth. So we won't really talk about the non-smoothness more today, but I just want you to start like thinking about sampling in these optimization terms. Like we have this KL divergence, it's a composite functional, there's a potential energy and entropy. We showed that this potential energy is really nicely behaved. It can be strongly convex and smooth based on our assumptions on V, but this function is non-smooth. That I'll maybe discuss more in tomorrow. All right, but if you combine the convexity of H with the convexity of this potential energy, or the strong convexity of this potential, then we've derived the following fact, which is like what does it mean for this KL divergence to be strongly convex in the space of probability measures? It's actually equivalent to just Euclidean convexity of the potential. Okay, so that's a pretty remarkable fact that here, like the Wasserstein geometry really reflects the Euclidean geometry. And this is related to what's known as the Bakr-Emery theory. Okay, and just like one sentence about what's the deeper connection behind this. So I've been talking about how Wasserstein geodesics are kind of a way of lifting Euclidean geodesics to the space of measures. You can do this whole story on manifolds as well. It turns out like if you can define a Wasserstein space over a manifold, and the geodesics between measures will, if you look at the particle level, they'll be following geodesics on your manifold. when you do these kind of like computations of the derivative of the entropy in that more general setting, what you'll find is like this convexity of the entropy, the fact that this Hessian was non-negative, this actually comes from the fact that Euclidean space is flat, has a non-negative curvature. But in general, on a manifold, if the manifold has positive Ricci curvature, it will imply that the Hessian of the entropy is positive on the manifold. So then this in turn like lets you kind of characterize the curvature, like the Ricci curvature lower bounds on your manifold in terms of these like properties of functionals on the Wasserstein space over your manifold. And then this lets you kind of generalize notions of curvature to non-smooth spaces. So this is like a really famous theory, like the Lott-Stern-Villani theory of synthetic Ricci curvature. So there's like a lot of interesting connections that go on here. Just a bit of culture, I guess. Actually, what should I erase? Okay. So this tells you like strong convexity of your potential gives you strong convexity of the KL, and strong convexity of the potential. This is what's usually, if you look at it at the level of the density, this is saying that your density is strongly log-concave. Okay, yes.
If I have understood well, you say that if the space is not flat, that equality, that equivalence you show is not true anymore, right?
Yeah, so the lower bound that you'll get on your entropy functional will be like the lower bound that you have on the Ricci curvature of your manifold.
And where do we use in the computation that we have done that the space is flat?
Oh, where did we use this fact that the space is flat? Well, first of all, like the computation I did is, I think, pretty special to Euclidean space.
Okay, we use that we are in a Reynolds.
Yeah, I guess like on a manifold, you would have like more terms showing up.
Okay, thank you.
Okay, so this is by just the definition of log concavity. We say that the density is log concave if like you write it as e to the minus v and v is convex. So this is like an important condition for convergence of sampling. We can also now like write down what this PL inequality is. So just as before, strong convexity of the potential is going to imply this condition, a PL inequality, but let's just try to write down what that means more clearly. So the PL inequality says that if you look at the Wasserstein gradient of the KL divergence, let's say at mu, then this should be at least twice the objective gap. So that's the definition of the PL inequality. And we computed what the Wasserstein gradient of the KL was last time. We said it's grad log mu plus grad b. And there's another way to write this expression. You can write this as grad log mu over pi, because pi is e to the minus v. So this is my personal favorite way of writing the gradient. And then when you plug that into there, the left-hand side becomes grad log mu over pi in the L2 of mu norm squared. And this quantity is called the Fisher information of mu with respect to pi. So this is like kind of it's related, but it's different from the Fisher information matrix that shows up when you do like natural gradient descent. You can kind of try to relate these two concepts, but yeah, I guess they're kind of only loosely connected. Okay, so this inequality that the Fisher information upper bounds the KL divergence, this is classically known as the log-Sobolev inequality. Or an LSI. And just as we had for optimization, it's possible for a log-Sobolev inequality to hold even if your potential is not strongly convex. So in particular, your potential might look like a, it might look bumpy like this, like a perturbation of a quadratic, and then it would still satisfy a log-Sobolev inequality. So this is also like really classically studied in infinite dimensional analysis. So this PL condition, we'll rewrite this as a log-Sobolev inequality, which says that the Fisher information, which is just the L2 norm of this density ratio, should be at least 2 alpha times the KL divergence. Okay, any questions so far? Yes.
What is the weakest condition the function has to fulfill to such that the log-Sobolev inequality holds?
What is the weakest condition?
Yeah, because you said that it's not necessarily strongly convex, but then what's the weakest you could accept?
I can't really say there's a weakest condition because there's not really like a very good characterization of when an LSI holds, but essentially like, so this is like the subject of functional inequalities, which is studied because for one thing, like these inequalities are a very nice way of proving concentration measures. They're useful in high dimensional probability. But what you can show is that these functional inequalities are a lot more flexible than the property of being convex, having a convex potential. For instance, like you can take your potential and add any bounded function to it, and you will still have a distribution that satisfies LSI. So that covers like things like this. If you take your distribution and push it forward by any Lipschitz mapping, then it will still satisfy LSI. You know, like there's like all sorts of like results like this in the literature that tell you when these kind of functional inequalities are preserved. So that's why like this constitutes a larger class of distributions. In particular, like even if you have very non-convex functions like this, it will still satisfy LSI. It's just that the constants are getting worse and worse.
So in general, is the Fisher information the LT norm of the Wasserstein gradient?
Yeah, this Fisher information relative to pi is the Wasserstein norm squared of the Wasserstein gradient of the KL.
And does it say if you were to change the functional, would that would still be the case?
No, so the Fisher information is specific to the KL.
Okay.
If you use a different functional, you would call the norm squared of the gradient some other name, I guess.
Okay. Okay. Right. Thank you.
Okay, so we've done this stuff in continuous time, but sadly, like in order to really understand sampling, you need to do the discrete time. So like one of the reasons why this is the case is that in continuous time, you can kind of arbitrarily speed up time just by like reparameterizing your curve. So if you really want to understand the computational complexity, there's no way around trying to understand the discretization.
Sorry.
Yes.
I'm sorry. It's a question which is a little bit from, I mean, back in time. But, I mean, a little too late maybe, but I'm not like seeing the condition that like the first red condition like there, because you said that alpha is less than equal than the nabla square with respect to the W2KL, right? So yeah, like the flow of thought, I think it's that we differentiated the KL divergence, right? With respect to the potential and to the entropy. And we found a bound for the potential and also bound for the entropy, right?
Yes. But
the bound for the entropy, like I'm not seeing, like, wasn't that the part like nabla square V less than equal than beta I? Like, I mean, I'm not seeing the bound on the entropy. Like,
the entropy bound was like up here. We just said it's convex. So lower bound on the entropy is just 0.
oh, I see. Okay. Yeah. Okay. So the lower bound on the entropy is just 0 because we showed it is convex. Okay. Makes sense then. Okay. Okay. So, and the bound on the potential is that one, right? Where we have bounded it from above and from below somehow.
Yeah.
Okay. Okay.
Yeah. So like more precisely, what I showed you is that if V is strongly convex, it implies the strong convexity of KL. I haven't shown you why the reverse implication holds, but that's also something that's known.
Okay, and saying, just to check, like saying that, I mean, I'm not getting like pi is strongly log concave. Like, what does this come from? Like,
so pi is e to the minus b.
Okay,
right?
okay. So distance.
So all this is saying is like if you take the log of pi,
okay, I see.
concave or something.
Okay.
It's just a standard terminology for what we call pi.
I see. Okay.
And also, hence the title of this course, log-concave sampling.
Thank you.
Okay, and like hopefully the intuition should be clear that like if we have a convex potential, it corresponds to a unimodal density. So this is the kind of density which is very easy for a diffusion like Langevin to explore, because it doesn't have to jump between two different potential walls. So this is just like reflecting our intuition. But the point is like this intuition that sampling is easy when we're in like a convex wall. This is really using like the Euclidean geometry of this potential. So we need to have some kind of geometric structure that really respects this Euclidean geometry to see that. As opposed to like if we just consider like the L2 geometry on the space of densities, then that doesn't see the Euclidean geometry at all, so we wouldn't arrive at this kind of convexity condition. Okay, so now I will start to discuss discretization. Okay, so what we're going to do is consider like the discretization of this diffusion, which is just going to be this algorithm. So my next iterate, I'm going to use like X for the algorithm and Z for the continuous time process. This will be my notation. I'm going to look at iteration K plus 1, but I'm going to denote this by K plus 1 times H. So the reason why is like if H is going to be my step size for my algorithm, and then K plus 1 times H is the total amount of continuous time corresponding to like the iteration of the discrete time algorithm. It'll just be helpful to like have the same notion of time between both the algorithm and the continuous time process, because we're going to compare them a lot. So the iterate at the K plus first iterate is obtained by, I look at the previous iterate. To discretize this gradient step, I will take a gradient step on the potential. And then I need to add the Brownian motion increment. So the Brownian motion increment is bk plus 1, h minus bkh. Okay, and the point is this is implementable because the increments of Brownian motion are independent and Gaussian. This is just a Gaussian with variance h. So it's very easy to generate this on a computer. So now I can fully run this process. And it's supposed to be a discretization of the continuous time process. So this is the Langevin algorithm. And then similarly, we have these conditions. these two conditions are going to be the analog of the ones we had in optimization. So here, like in optimization, we just assume that the potential is strongly convex and smooth. And we're going to use the same assumptions in sampling, which will imply like the strong convexity and smoothness of the potential energy. But when it comes to the PL condition, the PL condition in the space of measures is this log Sobolev inequality. So that's the assumption we place on our measure pi. And then we also combine it with smoothness on V. Okay, so let's start by analyzing the W2 case. Not sure I'll get to the LSI case. Okay, and also like the continuous time process, I denoted by pi sub t, and the discrete time process I'm going to denote by mu. Let's say, where should I put this? So xkh is going to be distributed according to mu kh. Okay, so what do I want to control for the discrete time process? I want to control the W2 distance between the law of the algorithm at the k plus first iteration and the distance in Wasserstein distance to 2 pi. Okay, so here's going to be the picture. We have a mu k plus 1h, which is at the particle level, it's the algorithm xk plus 1h. And then it evolves by the algorithm. Oh, sorry, this should be kh. It evolves by the algorithm to xk plus 1h. I guess I should probably make this more noisy. Okay, and then we also have the continuous time process z, which because we're going to consider like the stationary version of this process. So the stationary version of the process is always distributed according to pi. And then this guy evolves according to the continuous time diffusion. And then we end up at z k plus 1h. Okay, and then we're going to optimally couple these two random variables in the sense of Wasserstein distance. I'm not sure that will be. Okay, and then we want to, right, so this is at most, actually, how do I want to set up the couplings? Okay, essentially like, if we had optimally coupled this, then the distance between these two random variables will give me the Wasserstein distance at time kh. And then I want to say like x evolves according to the algorithm, z evolves according to continuous time, and then I want to compare how their Wasserstein distance evolve. But what's going to be helpful is to introduce an auxiliary process. So this auxiliary process is going to be, I start at zkh, but instead of following the continuous time process, I'm going to instead follow the algorithm. And I'll call this like x bar. And we'll say that the law of this is mu bar. Okay, it'll be helpful to introduce this because then we could just use the triangle inequality here. And introduce mu bar. Okay, so why is this helpful? It's because like for this first term, I'm looking at the difference between mu and mu bar. So that's the difference between this copy of the algorithm and this copy of the algorithm. So now I have two processes which are undergoing like the same exact dynamics. And then here we have like two processes which originated at the same point, but now it's like comparing the discrete time algorithm to the continuous time. So this is a discretization term. So how should we deal with this? Okay, so the Wasserstein distance is an infimum over all couplings of these two measures. So one way I can couple these two measures is just via this diagram here. So I couple xkh and this point optimally, and then I run them, and then I will get two random variables which are distributed according to the measures I'm looking at right now. But once I run the algorithm, like these two are no longer necessarily optimally coupled, right? But it's still some coupling, so I can still use it to upper bound the Wasserstein distance. This will be at most this difference. Okay, but what are these processes? Both of them are evolving according to the algorithm. So that means xk plus 1h. By definition, it's this guy. And then x bar is also evolving in the same way, but I'm going to start it at zkh. That's the only difference.
Sorry.
Yes.
I have a question. Like the first inequality, like I mean the expectation value is taken with respect to which distribution? Like in which sense? Like computational sense? So...
Like these are like two random variables that are coupled.
Yeah.
In fact, I told you the coupling. So the coupling is like I've coupled xkh and zkh according to the optimal transport plan between these two meters.
Okay. So there is a T basically that can send xk to zk.
Yeah, so that tells you how they're coupled at the start. And then I update both of them according to the Langevin algorithm.
Yeah.
But when I write down this equation, the fact that I use the same notation here means I'm also like coupling them such that I add the same Brownian increment to both processes.
Okay, makes sense. Makes sense.
So then I get these two random variables, and then I just want to compare this difference.
Okay. Okay.
So the nice thing about like choosing these Brownian motions to be the same is they cancel. So this is just upper bounded by this quantity. So now like notice like here I'm applying the map identity minus h grad v to xkh and also zkh. And then I claim that this mapping identity minus h grad v, this is Lipschitz with constant at most 1 minus alpha h if h is at most 1 over beta. Okay, so why is that the case? I could just differentiate this map. The gradient of this map is just the identity matrix minus h times the Hessian of v. And then this is so I know that v is between beta and alpha, the Hessian of v. That means this mapping is at most 1 minus alpha h and at least 1 minus beta h. But if I choose a step size smaller than 1 over beta, then this is going to be at least 0. So the Lipschitz constant is just going to be governed by 1 minus alpha h. Okay, so in the strongly, this is just like contractivity of a gradient step for a strongly convex function, which is also used in optimization. If I use this Lipschitz property, then I get a factor of 1 minus alpha h here. And here's where I use the fact that xkh and zkh are optimally coupled, because then this expectation is just the Wasserstein distance between ukh and pi. Okay, so this tells me that if I run 2 copies of the algorithm, then it's like a contraction in the Wasserstein metric. And this is using like the strong convexity of the potential. So you should compare it with the continuous time result, which was saying pretty much the same thing, that if the Hessian of your potential is lower bounded, then your diffusion is a Wasserstein contraction. Okay, so then we just need to bound the discretization error term. Okay, so remember both of these processes were started at zkh. It's just that one's following the continuous time process, the other is following the algorithm. So again, I can like upper bound this by just taking the coupling of these 2 processes. Where let's write out what these processes are. So this x bar is following the algorithm. So as I wrote before, it's zkh minus the gradient step plus the Brownian motion increment. Whereas the z process is following the continuous time diffusion. And here's how I can write the continuous time diffusion. This is equal to zkh minus the integral of the gradient between time kh and k plus 1h plus the Brownian motion increment. Okay, so that's the difference between the continuous time diffusion and the algorithm, is that in continuous time, I evaluate the gradient exactly at zt, and then I integrate this, but in discrete time, we have to evaluate the gradient only at the starting time. So then I just have to compare the difference between these 2, but again, like the Brownian motion cancels out. Yes?
Are we also in these 2 lines using the same noise term?
Yeah.
Okay.
I mean, for the proof, it'll just be coupling, convenient to choose this coupling. Okay. There are some situations where it's helpful to use different couplings. Okay, so now this difference, oops, I forgot the step size and the gradient. Okay, so this is just upper bounded by the expectation of the norm squared of this integral kh to k plus 1h of the difference of the gradients, grad v at zt minus grad v at zkh dt. This expression is also pretty intuitive. It's saying like the discretization error we made is just because like we use the gradient at time kh instead of the intermediate time. So this you can bound by, first of all, like Cauchy-Schwarz. Okay, so Cauchy-Schwarz is to bring this norm inside the integral. But because this integral is not an integral over a probability measure, when you apply Cauchy-Schwarz, you actually get a factor of h, which is like the integral over this time interval, times this expectation. Okay, so when you see this expression, the obvious thing to do is just to use the fact that the gradient is Lipschitz. That's our assumption of smoothness. So when you use the Lipschitzness of the gradient, this just becomes the difference between ZT minus ZKH. Okay, and then so this expression for Z that I wrote down here, if I just replace this K plus 1H by any like intermediate time T, then you still have the same expression. So I can just use that expression to plug this into here. And then what do you get? So ZT is equal to ZKH, which cancels with this, minus the integral of the gradient from KH to T. Plus the Brownian motion increment up until time T. And then there's a dt outside. Okay, so now I guess it's convenient to like split up this term and this term. So you can do that via like the triangle inequality. And then you'll have a factor of 2. Hey, like, by the way, like the calculations like on this board, they're kind of autopilot. You just kind of use all the obvious bounds, but I'll tell you when there's like something interesting to watch out for. This term plus then you have the expectation of the norm squared of this Brownian motion increment. But this is exact because we know how to calculate the norm squared of a Gaussian. So this will just be 2 times the 2 times the variance of this Gaussian times the dimension, which will be like the variance of the Gaussian is T minus KH, and then we're in dimension D. And all of this is outside. Okay, and this time is at most h. So if I first look at the Brownian motion term, what do I get? This is like d times h, but I also have an integral outside, which will give me another factor of h. And then I have this third factor of h. So this Brownian motion term will give me like beta squared dh cubed. Oops. Okay, this is fine. And then I also have this term, but again, we have to use like Cauchy-Schwarz to bring the norm inside the integral again. So I'll get another factor of h. Now I have the double integral kh, k plus 1h, kh to t, expectation of grad v of zs, ds, dt.
I have another question. Why don't the Brownian motion cancel in this case?
So like in this expression, like ZT is like farther forward in time, so there's like
okay, so we have different instances. Sorry.
Yeah. So when you have two processes evaluated at the same time, the Brownian motions cancel. But we already had one Brownian motion cancel here because we had the same time. But then once we did this calculation, we ended up with the process at two different times. So now the Brownian motion doesn't cancel. And this is actually going to be the term that dominates. But let's just like carefully bound this remaining term. Okay, so one very nice thing about this term is that ZS is the continuous time process. And moreover, I started the process at stationarity. So ZS is distributed according to pi for every time S. So this part doesn't depend on S, it's just the expectation under pi of grad V squared. Okay, so now this simplifies into the Brownian motion term, beta squared dh cubed, plus I have two integrals giving me like 2 extra powers of h. It's like beta squared dh4 times the expectation of the gradient under the target distribution. So this is all I have to bound now. So what is the right way to bound this term? The right way to bound this is to look at like the generator of the Langevin diffusion again. Let me remind you, the generator is a differential operator where if you apply it to any test function, it's the Laplacian minus the gradient of V and the gradient of phi. And the other fact that we had was that if you apply the generator to any function and you take the expectation with respect to pi, then this is equal to 0 for all phi. And we said this was like a characterization of the stationary distribution pi. Yes?
What is the letter after the 2 for t minus k h?
What is the letter? D?
Yes, this.
This one? It's a D.
Is that what is D?
The dimension.
Okay, perfect. Thanks.
Yeah. So this is a vector. The Brownian motion is a vector in RD, so you pay D. Okay, so this generator is like a really important part of studying Markov processes because it encodes integration by parts. So the like secret to solving PDEs is to just integrate by parts. And you can like discover a lot of interesting things just by playing around with this generator. So this will just be like one instance of what you can do with the generator. Yeah, so let's apply this to the function being the potential itself. That seems like a very natural choice. So what does this tell you? It tells you that the expectation of the Laplacian of V minus the gradient of V, inner product the gradient of V, is equal to 0. So the expectation of the norm squared of V, which is what we want to bound, is exactly equal to the expectation of the Laplacian of V. Okay, but what does smoothness tell you? Smoothness tells you that all of the eigenvalues of the Hessian of V are upper bounded by beta. And the Laplacian is a trace of the Hessian. So this is at most like beta times D. Then you plug that in, and then you get beta cubed dh4. But also remember that I'm assuming that h is at most 1 over beta. This is also the natural condition on the step size, because if you take a step size that's larger than 1 over the smoothness, then your diffusion could become transient. It's going to go off to infinity. So when you do that, you can actually simplify this, because you see like this this last term is just dominated by the first term. Okay, so this pretty much finishes the tedious calculation on the discretization term. And then we're basically done with the analysis. Okay, so going back to this triangle inequality that started it all, the Wasserstein distance at time k plus 1, h, pi, was bounded by two terms. The first term was this one where we obtained a contraction in the Wasserstein metric, 1 minus alpha h times the Wasserstein distance. And then we had this error term, which we bounded uniformly in time by like the square root of what I wrote there, because there I was bounding the squared Wasserstein distance, but here I have the unsquared Wasserstein distance. This is beta times d to the 1/2 h to the 3/2. Okay, so now you have this one-step inequality of how the Wasserstein changes from time k to time k plus 1. You have some contraction, but then you also incur an error. So now you need to iterate this inequality. And then when you iterate this inequality, then what you'll see is that the Wasserstein distance at iteration capital N is bounded by 1 minus alpha h to the capital N times the initial Wasserstein distance. Plus, I get this error term. But when you sum this geometric series, then I have to divide by alpha h. Yep. Okay. But let me just say that the Wasserstein metric is not scale invariant. Like if I scale the target distribution, like the law of the random variable, I scale up, and I also scale all these measures mu, then the Wasserstein distance will scale accordingly. So the scale invariant quantity in this problem turns out to be square root alpha times the Wasserstein distance, where alpha was the strong convexity. So if I write it in terms of the scale invariant quantity, I get the exponentially decaying term plus O of beta over alpha d to the 1/2 h to the 1/2.
Sorry, why alpha h appear in the inequality?
Why this one?
No, the other. Plus big O of, it was right. You divided by alpha h.
Right, okay, so what happens if I iterate this inequality? So here I paid like this error term, but now like let me plug in this inequality for this W2, and then I'll get another factor of 1 minus alpha h, but then I'll get plus 1 minus alpha h times this error term. I keep iterating, and what I'll get is this error term times 1 plus 1 minus alpha h plus 1 minus alpha h squared plus 1 minus alpha h squared cubed, and so on. So I will get
It's a geometric series.
Yeah,
okay.
It's a geometric series, and then when you sum that geometric series, you'll like divide by this alpha h. Okay, so if you compare this result with what we had, okay, let me just copy down this result. Okay, so if you compare this result with the one that we had for optimization, it seems like we did something wrong because we ended up with the extra term on the right-hand side. But that's actually necessary because when you discretize the Langevin diffusion, this is like a Markov chain in discrete time. So how do you know that the stationary distribution of this Markov chain is still equal to pi? So it's not. Like discretization actually changes your stationary distribution. When you let capital N go to infinity here, the first term vanishes because it's exponentially decaying. And then you'll just end up with this term. And this term kind of measures the Wasserstein distance between the like distorted stationary distribution obtained from discretizing and the true distribution pi that we wanted. So there's this like extra bias term that shows up in sampling. Moreover, like we have the problem dimension appearing here. So sampling like is like much more costly than optimization because the rates you get will like incur dimensional factors. And let's see like what the complexity bound, what is like the number of iterations that you need in order to make this quantity less than epsilon. So if I want to make this whole thing a most epsilon, then to make the bias small, I need to choose the step size small. So I choose the step size to be epsilon squared over beta d alpha squared. So that's what I'll take the step size to be in order to make that this term at most epsilon. And then I need to take n at least as big as, if you work out what this is 1 over alpha h times log of the initial Wasserstein distance divided by epsilon. So then if I plug in what the value of h was here, and I ignore the logarithmic terms, then this tells me that n is, to logarithmic terms, beta squared alpha squared d over epsilon squared. Okay, so the number of iterations that you need to run this process scales like linearly in the dimension. You also get like this kind of factor that depends on the condition number of your problem. So note that the final rate is scale invariant because I use this scale invariant notion of performance. And then there's also this polynomial dependence on 1 over epsilon instead of a logarithmic dependence. So this is reflecting the fact that your algorithm is biased. It's not converging to the correct distribution. So you need to take a really small step size. Are there any questions? Yes.
So would you be converging to the right distribution if you had chosen implicit Euler instead of explicit, or?
If we chose implicit Euler instead of explicit Euler. So that's a great question. I think I'll like defer that question for a little bit. But yeah, my intention is to like think a little bit more critically about discretization.
Mm-hmm.
Yeah, so I probably, definitely no time for this proof, but I'll just like write down under this assumption of LSI, like using a different proof, you can get pretty much the same kind of result. Just like you replace the Wasserstein distance by the square root of the KL. And why square root? It's because the KL divergence is basically a squared quantity. And it's already scale invariant, so there's no need to multiply KL by anything. Okay, so you can prove this, but yeah, I guess like the proof is kind of different, uses some new ideas. All right, let's conclude today with just a little bit of, I don't know, philosophical discussion or something. Yes.
Are there algorithm similar to this one that has a better rate, or this is okay?
Yeah, so there are algorithms that do better than this. Also, like in optimization, gradient descent is not optimal either. There's an accelerated gradient descent. But like this, since this is the most basic prototype for a sampling algorithm, it's good to understand this first. Okay, so let's just talk about optimization for a bit. So let's say I want to minimize V. Okay, then if I know that V, okay, so what can I do to minimize V? What I can always do is the gradient flow in continuous time. This works like without assuming smoothness of V. And I can also, but if I have smoothness of V, then I can use gradient descent, which is the, sorry. So this is explicit discretization. But as alluded to, there's like, if you don't have smoothness, then you can also, it still works if you use an implicit discretization. So the implicit discretization says that you take a gradient step, but this gradient is evaluated not at your previous point, but at the next point. So this means it's like not, it's implicit. You don't know what xk plus 1 is in closed form, so you actually have to solve for xk plus 1, so that makes it harder to implement this method. But this method is a lot more stable. You don't need smoothness. It will still converge. So think of these as our three tools. We have gradient flow, we have the implicit method. So this is also called a proximal method. So equivalently, xk plus 1 minimizes a regularized functional, which is the sum of V plus 1 over 2 times the step size times the distance to your previous point. Okay, so this is kind of solving an implicit, like a regularized optimization problem at every step. And then we have the explicit method. And this is also called the forward method in optimization, and this is also called the backward method. Okay, so these are kind of like our building blocks in optimization. And then in optimization, there's also composite optimization. So in composite optimization, we want to minimize the sum of two functions, f plus g. And then f, let's say, is smooth. And then like probably you want to assume convexity everywhere if you want things to be tractable. And g is non-smooth. And convex. So this kind of structure appears a lot when you have like regularized optimization problems, like you want to add the L1 penalty, for instance. So what do you do to solve this method? This problem, like the standard one is the forward backward method, which is also called proximal gradient. So what is the proximal gradient? I'll just write it here. The proximal gradient is you simply take an implicit step on the non-smooth part. So I take the, okay, I should say this can also be written as prox, the prox operator. So you take a prox step on the non-smooth function, and then you take an explicit step on the smooth function. And then this can be shown to converge. Okay, so what do we have in sampling? We also have this structure where we have like the potential energy and the entropy.
Why would you want to do the explicit time step for the smooth part? I mean, anyways, you don't gain anything, no?
Well, it's much cheaper to do the explicit step. right?
Okay, so in terms of cost.
So whenever possible, we want to do the explicit step. Yeah, and usually like this prox operator can only be evaluated if G is like really simple somehow, like the L1 norm. Okay, so my point is like we have the exact same structure in sampling where this potential, I told you if V is strongly convex and smooth, then in Wasserstein space, this functional is also strongly convex and smooth. This entropy, we said is always convex, but it's non-smooth. Now, we have this problem, but what are our ingredients? So this gradient step that we've been taking in the Langevin corresponds to the explicit step on B. So we can do an explicit step on B, but what about H? So to minimize H, what we've been doing is adding this Brownian motion increment. So notice like the Brownian motion, because it like the law of the increments are known exactly, like we can implement this increment exactly. So we're really implementing the Brownian motion like in continuous time. So what we've really been doing is running the gradient flow for H. That's what the Brownian motion is. So rather than doing this proximal gradient method where you do forward and backward, we've been doing a forward and a flow. So this Langevin discretization is was called by my friend and colleague Andre as the forward flow. I'll get to your question in 1 second. So in optimization, we know the forward-backward method is unbiased. Like if you run this algorithm, it will converge to the minimizer of f plus g. But this forward flow algorithm is actually biased in general. Like even in the optimization setting, if you try to run this forward flow method for composite optimization, it would not converge to a minimizer. So that's kind of what's going on there, but it's kind of, yeah. So then you try to ask like, okay, is there something else we can do with H? Like it's probably not a good idea to run a forward step for H because it's non-smooth. Can we do an implicit step? No, because if you look at what the implicit step entails, then it's like intractable. We have no way of implementing the backward step on the entropy. So in sampling, like we want to be able to do this forward backward, but we can't. The only thing we can do is the gradient flow, but it's actually like despite the fact that this is bad for us that we don't have the backward, it's still a little bit serendipitous that like the thing that we can implement in continuous time, this flow step, is the part of the functional where we need something that can handle the non-smoothness. So yeah, so in sampling, like we're biased, but we can get some convergence guarantee. And then what I talk about like tomorrow is like trying to like think about this problem in like a little bit more detail and coming up with a better way to discretize everything. Yes.
It's not possible for computing the backward to advance in the direction of the linearization. I mean, I have seen such kind of method actually. Yeah, I have used them. So you have the nonlinear, let's say, gradient. You linearize it. You advance into the direction with the implicit Euler that you can invert and so on. And then
so if you linearize inside the prox, then that is actually the explicit step. And for sampling, for the entropy, we can't implement either the explicit or the implicit. So let me just like write down what.
Sorry. One thing that maybe, I mean, you linearize, but you solve an implicit step. So you invert the linear operator. You know, like you have the implicit dependence on the right hand side. So you linearize and solve an implicit step in the linearized direction.
In the linear. So what I'm saying is like, if you consider argmin of this linearized step, let's say it's like g of x plus gradient g of x y minus x plus this thing. This thing like is exactly the explicit step. Right, so if you replace, so this is supposed to be like the linearization of g of y. So if you have g of y here, this is the backward step. If you linearize g inside, you get the explicit step. And for sampling, what we want to do is compute the minimization over all probability measures of the sum of the entropy plus, and then this becomes the Wasserstein distance. So like regardless of whether you have the entropy here or if you linearize, so this becomes h of nu plus the gradient of the entropy, which is grad log nu, times the transport map from mu to nu. Wait, sorry, nu to mu, minus the identity in the nu norm. Okay, so this would be the linearization of the entropy in Wasserstein space. Like neither of these problems is actually implementable because they still require some optimization over all probability measures, and we don't know how to do that.
Okay.
Can I? It's my turn for the question. Okay, sure. I wanted to ask, like, is it? I mean, does it make any sense to think about the fact that you are applying the random noise, like the basically the Brownian motion, as something that is capable of somehow enlarging your distribution, which is something that we know increase the entropy?
Yeah,
so that's why it works somehow. I mean,
so the noise, adding the Brownian motion, we know it's a gradient flow of the entropy in Wasserstein space. It's like a special case of the Langevin when the potential is 0. So because of that, we do know that adding this noise decreases the entropy. But the problem is like we have two parts of this objective, and then we're trying to like alternate between different methods for like each part of the objective. And in general, like this is not going to be an unbiased method for minimizing the sum of the two.
Thank you.